Understanding the I2C bus, the basics of serial communication between electronic devices. The Inter-Integrated Circuit Bus, or I2C bus, is a widely used communication protocol in embedded systems and electronics. It enables data exchange between multiple integrated circuits through a simple two-wire interface. The two lines consist of the serial data line, SDA, for data transmission, and the serial clock line, SCL, for synchronization. Both lines are connected to the power supply via pull-up resistors, since I2C pins use an open collector design that allows devices to share the bus directly. All connected I2C devices share the same ground. A key feature of the I2C bus is its support for multiple masters and multiple slaves, allowing flexible communication among devices without complex wiring. I2C operates as a packet-switched, single-ended protocol, transmitting data in discrete packets over a shared connection. Its simplicity and efficiency make it well-suited for short-distance communication within devices such as microcontrollers, sensors, memory chips, and other peripherals. Originally developed by Philips Semiconductor, now NXP Semiconductors, I2C has since become an industry standard due to its reliability, scalability, and ease of implementation. Each I2C slave device has a unique address, which allows the master device to identify and communicate with the specific slave device. The address is typically 7 bits long, so there can be up to 128 possible addresses. Less commonly, the address can also be 10 bits long for more devices. The master device initiates communication by sending a start signal followed by the address of the target slave device. Data is then transmitted in a synchronized manner, with the clock signal provided by the master ensuring that all devices remain in sync. The protocol supports both read and write operations, and devices can acknowledge receipt of data to ensure reliable communication. The simplicity of the two-wire setup and the use of addressing make I2C an efficient solution for connecting multiple devices in a system. The sequence of SDA and SCL signals in the I2C protocol defines how address and data frames are transmitted. Communication begins when the master device generates a start signal by pulling SDA low while SCL is high, followed by pulling SCL low. Next, the master sends the address of the target slave device in an address frame, with the most significant bit transmitted first. This address is 7 bits long, and the 8th bit specifies the transfer direction. A value of 1 indicates a read from the slave, while 0 indicates a write to the slave. The 9th bit is the acknowledge ACK bit. A low value here signals that the communication has been successful. After the address frame, 1 or more data frames follow, each consisting of 1 byte, with the most significant bit transmitted first. An ACK bit follows every data byte. For write operations, the slave pulls SDA low to acknowledge receipt. For read operations, the master pulls SDA low to confirm it has successfully received the data. Once all transfers are complete, the master issues a stop signal. It first releases SCL, then releases SDA. This indicates that the communication has ended and the I2C bus is free. The data on SDA is sampled when the SCL is high. The I2C clock speed refers to the frequency of the SCL signal. In standard mode, it typically operates at 100 kHz, while in fast mode it runs at 400 kHz. The following diagrams show examples of I2C write and read operations. Data on the SDA line is sampled when the SCL signal is high. In the write sequence, the slave device address after the start signal is 1001001 in binary, which corresponds to 0x49 in hexadecimal. The 8th bit is 0, indicating a write operation. The slave then responds with an acknowledgement bit, 0. The following data frame is 00001000 in binary, or 0x08 in hexadecimal, transmitted from the master to the slave. The slave again acknowledges with a 0. The sequence ends with a stop signal. This process writes the value 0x08 to the slave device at address 0x49. In the read sequence, the slave device address after the start signal is 1001000 in binary, which corresponds to 0x48 in hexadecimal. The 8th bit is 1, indicating a read operation. The slave then responds with an acknowledgement bit, 0. The next data frame is 01000100 in binary or 0x44 in hexadecimal, transmitted from the slave to the master. The master acknowledges with a 0. The sequence concludes with a stop signal. This operation reads the value 0x44 from the slave device at address 0x48. When the master transmits the start signal, all slave devices listen for the subsequent address on the SDA line. If a slave device detects a matching address, it responds by pulling the SDA line low to acknowledge. An I2C slave device may have multiple predefined addresses, which can be selected by configuring the address pins either high or low. This feature helps prevent address conflicts among slave devices. Using the digital temperature sensor LM75A from NXP as an example, it is an I2C device, and its slave address is set by the digital inputs on pins 5, 6, and 7, labeled A2, A1, and A0. These pins can be pulled high to the power supply, logic 1, or low to ground, logic 0, or they can be controlled by digital signals from a microcontroller's GPIO. The 3 bits correspond to the least significant bits of the device address, while the most significant 4 bits are fixed as 1001. This allows the LM75A to use any address from 0x48 to 0x4F. An I2C slave device contains registers for configuration, status, and data. These registers have specific subaddresses within the device. Additionally, the slave device includes a pointer register that holds the address of the register the master device is communicating with. The first step in using the I2C peripheral is initialization, which involves enabling the I2C module and configuring the clock rate, typically 100 kHz for standard mode or 400 kHz for fast mode. After initialization, the device can perform either write or read operations. For simplicity, data is represented here in bytes. The following pseudocode demonstrates how to send data to a slave device. The write cycle begins with the start signal, followed by an address byte. The 7 most significant bits represent the device address, and the least significant bit is set to 0 to indicate a write operation. The first byte sent after the address specifies the pointer register, which selects the target register within the slave device. The next byte contains the data to be written to that register. Some slave devices include an auto-increment feature for the pointer register, automatically advancing it to the next register after each byte is received. This enables the master to transmit a continuous stream of data to consecutive registers in a single write operation. The stop signal is sent at the end of the write cycle. The pseudocode for receiving data from a slave device is similar to that of the I2C write operation. If the value in the pointer register is unknown, a preliminary write cycle is required to set it before initiating the read cycle. The read operation begins with a start signal, followed by an address byte where the 7 most significant bits specify the device address, and the least significant bit is set to 1 to indicate a read operation. The master then switches to read mode to receive data from the slave device. The number of bytes to be read is determined by the master and should follow the slave device's specifications. The auto-increment feature is also supported during read operations, allowing sequential data retrieval from consecutive registers. The read cycle concludes with a stop signal. The pseudocode presented here is intended for a high-level programming environment and assumes that hardware driver support for the I2C peripheral is available. The I2C bus provides several advantages that make it a popular choice in many applications. Its simplicity and efficiency make it well-suited for short-distance communication, particularly within a single device or circuit board. With only 2 wires, it reduces both hardware complexity and cost, while its ability to connect multiple devices on the same bus enhances scalability. I2C is also widely supported in embedded systems, making compatible components and development resources readily available. However, the protocol has some limitations. Its data transfer speed is relatively low compared to alternatives like SPI, which can be a disadvantage in high-throughput applications. The communication range is short, making I2C unsuitable for long-distance data transmission. In addition, systems with multiple masters can be more complex to manage and prone to conflicts. Therefore, understanding these advantages and limitations is crucial when determining whether I2C is the most suitable communication protocol for a specific application. I2C is widely used in applications that require efficient and reliable communication between multiple components. One of its most common uses is connecting sensors to microcontrollers, enabling real-time data collection in systems such as environmental monitoring, robotics, and wearable devices. EEPROMs often rely on I2C for data storage and retrieval, offering a simple solution for non-volatile memory in embedded systems. Real-time clocks, RDCs, use I2C to provide precise timekeeping for devices like computers, industrial controllers, and consumer electronics. Display modules such as LCDs and OLEDs also utilize I2C to receive commands and display data. Thanks to its flexibility, low pin count, and ability to support multiple devices on a single bus, I2C has become a standard communication protocol across a wide range of applications, including consumer electronics, automotive systems, and industrial automation.